Thanks for attending our webinar, everybody. The webinar on Save Time by Getting Off-Grid Right the First Time. This is a joint webinar between Morningstar and SunWize Power and Battery. My name is Mark McHenry, and I'll be your moderator for this session. Before we start, let me remind all attendees to type any questions into the question chat box at the bottom of your GoToWebinar pane, and we'll address them at the end or via text during this webinar. And if we can't get to them, we'll get back to you via email after the webinar. And we're going to be recording this broadcast and emailing you a link to the recording before the end of day tomorrow. We've also included a copy of this slide deck in the handout section of your GoToWebinar pane that you can go download right now. So let's go ahead and introduce today's speakers. So I'll advance to the next slide. And from SunWize, we have Errol Rankin and Grayson Klum. And from Morningstar, we have Brad Burwald. They'll each tell you a little bit about SunWize and Morningstar, and they'll share some useful information about what you need to consider and plan for before you successfully deploy an off-grid system. So Errol, you're up first, so please go ahead and start your portion of the presentation.
Thank you very much for the introduction, Mark. Very much appreciate it. I'm Errol Rankin with SunWize Power and Battery. And so today we're going to talk a little bit about the system size and side of things. SunWize has been around for 25 years doing off-grid design build projects. We have installations on all 7 continents, but primarily focus on serving North America. You can see a list of the products and services that we offer below. Our primary fulfillment and warehouse and manufacturing facilities are located on the West Coast and the East Coast in Oregon and New York. And I'll now hand it over to Grayson for the first portion of the presentation.
All right, thanks, Errol. Hey guys, my name is Grayson. I'm the product engineer here at SunWize. I'd like to thank everybody for joining us today. Today, SunWize will be going over the loads, solar modules, solar mounts, and the battery sections of a solar system. Morningstar, of course, will handle the charge controllers. So let's get started with what I think is the hardest, or at least definitely the most variable part of the solar system, the loads. It's worth pointing out that Errol and I will be putting up some of these links on some of our slides to either previous webinars or other helpful documents we would highly encourage everyone to check out after the presentation, because each topic we're about to cover really has enough information to fill today's full-time slot on their own. So we're just going to burn through as much as we can, and what items are relevant to you and your situation, I would definitely visit in more depth and probably more eloquently worded links that we are providing in the slides for more info. And these slides will be available to everybody afterwards, I believe. So as far as what I'm going to cover for these loads, or as far as loads go, how to think about loads and where your brain should immediately go, and a little bit about what we will want from you when you contact us. Load duty cycle, nominal voltages and tolerances, and then when I'm done talking, Errol has a really nice in-depth example that he's going to show just how complicated loads can be, which will hopefully be helpful for everyone tackling those complex situations. So a good rule of thumb, next slide, Errol, please. A good rule of thumb would be that the size of the load directly drives both the physical size of the system and the power size in a nearly linear fashion. So, for example, if you're in an area that gets a lot of sun, like Texas, and you've got a load of around 20 amp hours a day, then you're looking at around a 300 watt module. In the same spot, a load of 40 amp hours a day will need about a 600 watt module. Which would also mean you need a mount for those modules that is about twice as large as well, or potentially just 2 of the same mount. Either way, you're using twice the footprint. Same goes for ground mount. You need twice the ballasting, twice the space, etc. keep this in mind when determining what is your limiting factor. I'll talk a little bit more about size constraints in a couple slides. But as far as defining your load, it is absolutely critical that the load you would like to power can be accurately modeled. Can't stress enough that whatever you can do to define the load more than just reading the label that says 3 amp 24 volt will be really helpful in getting the most accurate sized system for your load, which will end up saving you money in the long run. For each load in the system, try to consider these bullet points, whether the load runs continuously, meaning 24/7, or non-continuous, aka a duty cycle, whether the load has a standby mode for low power draw. Consider any efficiency losses it may have converting from the system voltage to the load voltage, like DC to DC, or an AC to DC converter. Surge load, temperature can also play a big factor, more so related to batteries, but high temps also decrease the efficiency in those AC-DC or DC-DC converters. I mean, modeling a load is tough enough because without having an example system out there with current monitoring or an installer who can, physically clamp on a meter, sizing the system is really a padded guess based on the manufacturer's data sheet, those points. But even that number can be really misleading. So what we like to do to help get the most accurate load definition is work in amp hours per day. This chart is a snippet from one of our complete solar packages, our Power Ready Express systems. The darker colors on that world chart indicate a higher amount of sun hours, which we then use with this slide to find the array size you'd need to power the load. So, for example, in Texas, on that world example or that world chart, the peak sun hours per month there is about 4 to 5 amp hours per day. We can say 4 amp hours just to be conservative. And if you look in that 4 amp hour column on the right, if you just go down the line, the fourth one down there for a 20 amp hour load will get you about a 325 watt module, that fourth one down there. And then if you just double that, a 20 amp hour per day load goes to a 40, you'll get around a 650 watt module, exactly double the system actually. But these tools and the rule of thumb, sun hour chart, are really only valid when the load is well defined to begin with. So after asking yourself those load definition questions, question 1 on that previous slide was, is it a non-continuous load? And that means if it's not running 24 hours a day, 7 days a week, then it's going to have some sort of duty cycle and need to be further defined. These are a couple of real world examples actually. We have a few test systems around our facility here in Oregon. One of them runs a 2 amp continuous draw LED exclusively at night. So the question is for this, about what size solar module or combination of modules should we be using? And assuming nighttime is about 10 p.m., 6 a.m., 8 hours times a 2 amp continuous draw of light gives us 16 amp hours per day. Referring to that previous chart, we find that Oregon would be in the orange column for only this 3 peak sun hours in the weakest month. We don't get a ton of sun up here. And dropping down that column to these, looking for 16 amp hours a day, it's about the 15, again, that fourth row down for a 24 volt load. And in this case, it was a 24 volt LED. But if it was 12 volt, you might be able to get away with the 150 watt module above that one. So the second example that we have here is a super common case of why it's so important to understand your load. Say you've got a radio with transmit power of 100 watt and the standby power is 10 watts. Radio transmits for about 2 hours a day, and then the rest of the time, the other 22 hours, it's on standby. We can start by getting amps by dividing the 100 watts by 24 volts, then multiplying by 2 hours a day, and we're left with 8.33. Divide the 10 watts by 24 times 22 gets us the 9.17 amp hours a day. Sum those guys up, and you are left with the 17. In this case, if the load was only defined as 100 watts for 2 hours, the system would be undersized by almost half. I mean, in the end, the standby power ended up consuming more than the actual use when you're transmitting. So we will often work with customers who have larger loads to define a load spreadsheet actually in Excel, which can be really helpful in clarifying in both sides the scope of what we're working with. So once you know how much power you need, jump to the next one, Errol. You've got to make sure that you have enough space to build it. And sometimes with these large systems, especially if you're on mountaintop or oddly defined plot of land, which happens more often than not, there just isn't enough space to work with. And when land runs out, hybrid systems become a really great option. Errol will dive into that in a little bit, but some other big space considerations to look out for would be placing the array away from the shade, which is a little less obvious than it sounds, and in a place with low wind. Try to stay away from the coast or, flat desert. Sometimes it can't be helped, but it usually adds complexity and cost. Of course, these will also be sized for worst month and tilted for the worst month as well. Array shading, I will again defer to a great white paper we have on module shading on our website. But basically, here's the gist. Don't expect to walk out to your site in July and think, oh, nothing but tiny shrubs, lots of sun up here. Because what people don't think about is future plant growth. When these batteries are maintained and the modules stay pretty clean, solar systems can last a long time. 10 years can go by just like that. All of a sudden, those shrubs creeping up sides modules, that tiny tree that was there in that first site visit is suddenly casting a longer shadow. And as you can see in these pictures to the right, module photocells, even if just one of them is covered, the entire panel output will end up being 0 watts. A very frustrating concept for everybody, but the pictures really illustrate what shading could look like. Even when just 1/2 of a cell is covered, that means that in a series circuit, only half of the total current can be produced in that cell. And since in a series circuit, the current always stays the same, the total output then has to be half because just that one cell is covered. Very frustrating. Next, I want to cover module stringing and mounting. We can't talk about stringing modules without mentioning the Morningstar string sizing tool up here in the top. We use it pretty much with every system that may be pushing the boundary for one of Morningstar's controllers. Super quick and easy check. I'm sure Mark will go over it in his slides. But the main topics when it comes to using multiple modules are the array voltage compared to the system or the battery bank voltage. Module connectors, I'll very briefly go over array sizing. And then just remember that if you have 60 cell modules, you've got to have an MPPT controller. Then we'll also take a look at some mounting options pending the array wattage that you need. So the battery bank voltage is determined by the most dominant load voltage. For these larger, or for a larger system, 150 watt plus, the system will most likely be made up of 72 cell 300 watt plus modules connected in series, then wired up into about 48 volt configuration, put into parallel in a combiner box, or using 2-to-1 connectors. We are a huge fan of these MC4 connectors in the picture on the right, mostly because they make connecting modules in series or parallel so easy. For series, you just connect positive of one module with the negative of another. I'm sure the installers are rolling their eyes, done it a million times. This picture shows modules in parallel, but with a 2-to-1 MC4 connector, where you connect both of the positives to one connector and both of the negatives to the other. And they make these connectors really foolproof because the connectors will only fit in the positive or in the negative. Voltage drop is another important consideration when the array is far from the battery bank. The array voltage must always be greater than the battery bank to charge. So a couple of volts can really make a big difference, actually, especially if you have sensitive load or inverter that those need to be kept close to the source for them to operate properly. Voltage drop will increase with increasing wire length and decrease with a larger wire size. Just good to keep in mind. Last thing I'm going to cover real quick is a few mounting options for the solar system. Side of pole mounts shown on the right. It's actually one of those test systems I mentioned earlier with the LED light on the top. And then skid mounts, like the picture on the left, are great for being portable, and assembly is pretty easy since they're on the ground already. You don't have to mess with getting on a ladder or put on a pole. SunWize is actually about to release a skid mount that can fold completely flat, being only a couple inches high, which makes for it's really great for rapid deploy situations. A pro and a con to these skids, though, is they tend to be really light, and the foldable one that I mentioned is only around 30 pounds. So sometimes these need a lot of ballasting or extra weight in addition to the enclosure. Sometimes you've got enough battery in there and it does the job by itself, but also consider the ballasting that you'll need. The mount pictured here is actually on one of our super heavy steel galvanized skid bases with eye-hook attachment points for easy lifting into place. This mount also works with our normal ground mounts. Those ground mounts don't necessarily need this base. They can also just be bolted straight into a concrete pad. We've also got top pole mounts, power stations. Power stations have been really popular lately. They're basically two steel galvanized A-frames that can hold up to 12 modules apiece. These are really expandable too. You can throw 2 or 3 of these or more, however many you need, cover your load. But it usually ends up being a size limiting factor with those. So then I think, yeah, I've got enough. Here's a breakdown of approximately what power ranges these mounts can handle. SunWize side of pole mounts can handle 1 to 3 modules. Enclosure fixed ones generally only work with one type of mount, the smaller ones, so it's pretty limited range. Skid mounts cover up to 2 of those 72 cell modules. Top pole mounts can get pretty huge, 10 modules-ish. And then, like I said, the power station can hold up to 12. And of course, all of these can be doubled, tripled, whatever you need to accommodate if one mount just isn't cutting it. With that, I think that's all for me. Thank you all for listening, and I'll hand it over to Errol.
Thank you very much for that, Grayson. I appreciate it. So before I jump into this next section and talk about a little bit on the system design side of things and then batteries, I want to mention that SunWize actually has a couple of application engineers that are moderating in the background and available on chat. So if anybody from the presentation has questions from either the last section that Grayson covered or anything that I'm about to cover, I encourage you guys to type that into chat and dialogue and converse with application engineers that are available to hopefully answer some of the questions that you guys may have. And then when we get to the hybrid section, we have somebody else that will be available to answer some questions for that also. So as Grayson mentioned, many of the details from this presentation can be cross-referenced in our tech notes and webinars sections on our website. If you go to our homepage, you can simply click on the Explore menu item to access those. So as was also mentioned, the discussion today will be around off-grid, mostly industrial applications where we size around the worst case month for year-round operation, as opposed to designing to maximize the average annual energy production. This is why you'll notice in our example, the solar global horizontal insolation, or the solar resources, are listed for December rather than the average annual. So on the right-hand side, we have an example load scenario, and that we'll look at in a diagram view in a moment as well. So we basically have a 4-port PoE switch that's powered off of AC, and off of that we have 4 PoE devices that are listed here. We also have a 24-volt load circuit with a voltage tolerance of plus or minus 0.5 volts for each one of those loads. So depending on how you add up these various loads, you can get any of the answers that are in the red box to the left, which is meant to highlight the importance of understanding your load profile and not getting that part wrong. So here in this diagram, we can see the load profiles that we were just discussing visually. The solar system is at the top. We've got our AC load circuit on the left, powering our PoE switch, which in turn is powering the 4 PoE devices. And then on the right-hand side, we've got our DC load circuit for our 4 24-volt DC devices. Now, if we include voltages, efficiency losses, and load values, things become much more clear. Now, a common issue is differentiating loads between devices that also power other devices, which is common in PoE applications, but can occur in other places too. Another frustration that Grayson mentioned was when we only have, for instance, a maximum load value to go off of from the manufacturer's datasheet rather than an average or some real world information. So you'll notice here on the right, we've put in this DC-DC converter. And the reason for that is because of that tight voltage tolerance of plus or minus 0.5 volts, which is too narrow to be able to run off of the battery bank directly. If that would have had a wider voltage window, we may have decided to design the system at 24 volts DC rather than 48 volt DC. However, in this case, you can see we have our AC load circuit with our 93% efficient inverter and our DC load circuit with our 85% efficient DC-DC converter. You can see that we've identified the internal power consumption of the PoE device at 14 watts, the PoE switch, and then we have the 4 endpoint PoE devices that we listed and their rated power consumption, and then we've got the DC devices and their power consumption. Looking at it in this way, it becomes clear that the answer to the previous question was 154 watts. Okay, so at the top of this slide, you'll notice that there's a direct URL for our basic system sizing webinar, which can be used to cross-reference a lot of the information in this slide, as obviously there's a lot to unpack. I'm just going to focus on a few key areas right now. The first thing that I want to point out is this load information highlighted in green of 81.3 amp hours per day average at 48 volt DC. Now, this is a great example to be able to run through the conversion that Grayson touched on from that 154 watts continuous to 81.3 amp hours per day at 48 volts DC. Now, the reason for this is because once we have the load in amp hours per day, a few things about the system design will fall into place much easier. So the first thing is that, again, from this webinar, you can look at the sizing equation for your solar array based on your load. So we can take the right tilt angle solar resources for this site, which is typically latitude plus 15. So that's the tilt angle that we want. And that happens to be 3.5 kilowatt hours per meter squared per day average for December. So if we take that plus a design input assumption around our array to load ratio, or our minimum ALR, in this case being 1.4, along with the module max current rating, or IMP, which in this case for the 355 watt module we've selected is 9.16 amps, along with system losses of about 10%, you can quickly calculate that the number of module strings that you need in the array is 3.9. Now, obviously we need a whole number and we need to round up to be conservative. So that gives us 4 strings of solar modules. Now, since each one of these solar modules is 24 volts, we've got a 48 volt system. That means that there's 2 modules in series, 4 strings in parallel, which gives us 8 modules in total. At 355 watts, that's where we get our 2.84 kilowatt solar array. Now, moving on to the battery bank side of things, you can see that we've sized our battery bank at 530 amp hours per day at 48 volts, and we've got our load of 81.3 amp hours per day. Now, if you divide 530 by 81.3, you've got 6.5 days, right? Well, wait, why does our battery days at ambient say 5.2 days? Well, the reason for that is because of the 80% depth of discharge setting that we put for the low voltage disconnect on the charge controller, which we'll talk about in our next section regarding the batteries. Then, when we're considering the temperature conditions for the site in question, which is Casper, Wyoming, at 0C, this battery autonomy is actually 4.5 days, which again, we'll cover. And finally, when you consider the end of life capacity degradation of the battery, it may only be 80% of its original capacity at the end of the life. So we need to design for that as well. So now we're looking at 3.6 days of autonomy. And using that information along with the needs for your project or application, you can start to determine what the appropriate size and design is. We're here, of course, to help you guide through this process and arrive at the best answer for your applications. So looking at the question in system, we had 8 large format modules, and you can see on the left-hand side, we have a top of pole mount with 8 or 9 large format modules. So that's about the footprint of the array size that you'd expect for this system at about 154 watts continuous. In the middle, this is a power station, SunWize power station frame that Grayson was mentioning. This one is holding 8 large format modules with an integrated battery chest enclosure in the back, which is shaded. And then on the far right, you can see again, in this particular example, we've spec'd out 8 group 8D batteries, 2 strings at 48 volts to give us that 530 amp hours with a TriStar PWM charge controller and as another TriStar as the load controller to give you an idea of the footprint, size, and form factor of this particular example. So here we have our system variables checklist of things that we want to keep in mind and review. This is going to be available with the presentation, so I encourage you guys to reference this. I just want to point out a couple things about this. On the first point, these ALR or array to load ratio ranges, which is the ratio of energy produced by the array to the amount of energy consumed by the system, along with the battery autonomy. More information on that can be found from our tech note on IEEE 1562, which is actually covers the best design practices and is the only official standard for off-grid system design. And then I want to touch briefly on that third bullet point again about remote monitoring. And so, you know, this is a major design decision in your system, and a couple things may really dictate that. The first being whether or not you already have networked internet on site readily available. And the second being whether or not you're going to have cell phone reception at your site in order to be able to broadcast that remote monitoring. So we're going to move on and talk next about batteries. The reason is because they often represent up to 40% of the cost of the system and are the only component that can, and in some cases 100% will, fail simply from doing nothing, i.e. prolonged time in a low state of charge. This makes them particularly vulnerable compared to other components in the system. Now, the approximate life range for maintenance-free VRLA batteries in solar applications is about 3 to 7 years. If you're under this range or not at the right edge of the range for your application, you should be asking questions about why. So another thing I want to talk about is matching the expected battery life with your project application. So we typically don't suggest using a battery that's rated for 5 to 7 years of life in a project that will only last 2 years. Or conversely, using a battery that's only rated for a 3-year life in a project that will last 5 to 7 years. Now, because these batteries are such an expensive part of the system, representing up to 40% of cost, it's easy to make decisions up front about saving on capital costs, but then instead end up paying for it down the road in OpEx expenditures. So definitely be mindful of this balance when making decisions. Also consider beyond just the datasheet information, things like testing standard, quality control, and other information about the batteries that you're choosing. So the next thing we're going to cover is solar battery basics. And the most important thing to remember here about VRLA batteries is that leaving them at low states of charge damages them. The lower the state of charge and the longer it's left in that state, the more likely the damage is irreversible due to sulfation of the plates. This is why we utilize the 80% depth of discharge low voltage disconnect set point that we talked about in our example to protect the battery if it does get deeply discharged. Now, even at that 80% LVD, if that site is not addressed when that happens, and if there is prolonged cloud cover, shade, other situations, if it's not properly designed and that battery sits there for an extended period of time, you can still potentially permanently damage and ruin your battery bank, even with that LVD set point. So do keep that in mind. Now, on the right, you'll see a typical 3-stage charging diagram. You'll hear this 3-stage charging referred to a lot. That's bulk, absorption, and float. Now, the first stage, bulk charging, is where the majority of energy in the battery is acquired, and it happens very quickly. It can be up to 80 to 90% of the total energy in the battery occurs during this stage. However, reaching the absorption stage with the right frequency is very important for long-term battery health. Even though compared to the bulk charging stage, it's a much smaller percentage of actual energy that is being delivered. So another thing to keep in mind is that batteries do self-discharge. So if you've had a project or a system or batteries that have been in your warehouse for a long period of time and they have not been topped up or addressed or touched for say 6 months or a year before they're sent out for field deployment, that can have a major effect as it can be up to 2 to 3% capacity loss per month. So finally, we want to talk about this end of life factor for the batteries that we mentioned in our system design example. And that is that batteries will lose some capacity over the duration of their life. They may be at 80% of their original capacity when they're near failure. Therefore, we want to apply this in our design to make sure that our assumptions hold as accurately at the end of the system life as it does at the beginning, or the end of the battery life. So the next topic we're going to cover is temperatures and their effect on batteries. So cold weather reduces available energy in a battery. Recall from our example, our 5.2 days of backup at ambient became 4.5 days of backup at 0 degrees C. Now, in addition to that, batteries can also freeze. As the state of charge of the battery drops it becomes more susceptible to freezing. So at the extreme case of -40°C, which is about the lower range that VRLA batteries are typically rated to operate, the battery can operate if it's at 100% capacity, but it will freeze at this temperature if the battery reaches 75% capacity. At 50% capacity, the freezing temperature will be higher, and so on. So both of these cold weather factors must be considered, which can result in very large derate factors. These effects make fuel cell hybrid systems in cold climates that much more advantageous, which we'll talk a little bit about. Now, I also want to mention lithium batteries and the fact that typically they're only rated for operation down to about 0°C. There are, of course, exceptions. One of them, just as an example, being the LT series by Relion, which works down to -20°C. So finally, we want to talk about the effects of hot temperatures. Generally, life of the battery decreases by 50% for every 10°C above 25°C. So a battery that's rated to last 5 years at 25°C will only last approximately 1.25 years at sustained temperatures of 45°C. That's because it's 20 degrees higher above 25°C. 50% of 50% is 25%. 25% of 5 years is 1.25 years. Of course, ambient temperature does not always equal battery temperature, so keep that in mind as well. So here we're going to talk about preventative maintenance, or why would I replace a battery early if it still works? There are many good reasons for this, some of which we've outlined here, but I want to focus on one reason in particular, which is confusion over whether batteries have actually failed and how difficult this can be to do in the field with time constraints, limited knowledge, and perhaps bad weather. So this is a great opportunity for us to introduce how to measure a battery's state of charge. So if you're looking at this table, you may be thinking, all right, that's straightforward. I got this. I'm going to come up with my multimeter and I'll have an answer on what to do. But if you read the text at the bottom in red, it says the true open circuit voltage of a battery can only be determined after the battery has been removed from the load, charge or discharge, for 24 hours. Testing under load often results in bad information. Now, disconnecting batteries from the load and letting them sit for 24 hours is impractical for many field situations. And even then, a full discharge test under known load will typically be the final verdict on the state of the battery and whether it can really hold a charge despite what the open circuit voltage says. So one other thing to keep in mind is sometimes there are weight constraints on batteries due to air shipping requirements or something like that. So if you're forced in a situation to use a smaller group size battery than you otherwise would, you may be in a situation where you need to put in more than 4 strings of those batteries in order to reach your autonomy requirements. Now, because best practice is 4 strings of batteries in parallel or less, one kind of nifty workaround is that you can use a DC source isolator to actually get 2 separate groups of strings that are DC isolated and can ultimately be used to get you the autonomy that you need while protecting the health of the batteries. That can also come up when you're in a transition between group 8D batteries and 2-volt industrial interlocking style batteries, where it may be more practical to use, say, 8 strings of group 8D batteries rather than something else. So we're going to move on to battery charging set points. You'll see that there's a ton of information in this chart that covers a range of battery types and all the various scenarios, but I want to focus on the sections in blue. So you'll see we've got our gel and AGM monoblock batteries, and we've got our bulk charge stage, and then we've got our voltage set points for our absorption stage and our float stage. Notice that in the bulk charge state, it lists a max current rate, which we'll talk about here in a second. And then at the bottom, we have our temperature compensation value of -3 millivolts per cell per degree C. Now, some chargers have a fixed temperature compensation voltage, like -5 millivolts per degree C per cell, and others might have an adjustable set point. If you have an adjustable set point, that can be matched to the exact battery's manufacturer specifications, which can help in your system longevity. This is also why we have remote temperature cables. So if the batteries are in a separate enclosure from the controller, the charge controller can sense what the actual battery temperature is to apply the right temperature compensation. In reality, typically a series of dip switch settings or other programs on the charge controller will be set for a specific voltage chemistry combination, and you won't think about it and you'll be on your way. However, lithium batteries are typically less consistent or forgiving with their battery management system and variable designs, which is why the Energy Storage Partner Program from Morningstar is so great, because it gives you real-world experience and information about the compatibility between the lithium battery and the charge controller. So going back to this max charge rate for the bulk charging stage, it says C20 at 1.72 VPC or 6x I20 at 1.72 VPC. So what do these mean? So the first thing that we need to understand is that C20 is a measure of the capacity of the battery. And the quicker that the battery is discharged, the less capacity there will be, and the longer it's discharged, the more capacity there will be. So the C10 rate will be a smaller capacity than C20, while C100 is greater. In our example, we've chosen a battery that has 100 amp hour capacity at the C20 value. So looking at these rules, 30% of 100 amp hours in a current rating is 30 amps. Now, the I20 rate is the amount of constant current required to entirely discharge the battery over the hourly subscript, which in this case is 20 hours. So 100 amp hours divided by 20 hours is 5 amps. 6 times 5 amps gives us that 30 amps value. This is our max bulk charge current into the battery. So here's again our battery variables checklist that I encourage you guys to go over and utilize in the future for your various projects that touches on a lot of the topics we talked about today. So the next thing I want to talk about is hybrid systems. In particular, we're going to be covering fuel cells and one particular solution, which is the EFOY series of fuel cells that both SunWize and Morningstar have familiarity working with. We actually have a representative from EFOY available, so if you have further questions on these sets of slides for the rest of the presentation, I encourage you guys to put that into chat and hopefully be able to cover that. Now, the potential challenges are the questions that the customers and engineers would need to ask themselves before installing an EFOY system, and that's on the left in the gray boxes. The proven EFOY benefits are how we solve these challenges and are the green boxes on the right. Now, as an example, a Pro 2400 EFOY unit with 2 M28 fuel cartridges can provide up to 12 months of continuous power output for a 60-watt standard load. This setup gives you 100% reliable power with a weather integrated system from -40F to 122F. So at the top here, you'll see this EFOY fuel cartridge that we're talking about, which makes it easy to swap, as well as a picture of the EFOY Pro series and the battery. Now, the voltage graph on the bottom, you'll see from 0 to 14.2 volts will dictate when the fuel cell unit turns on. So it can be programmed to automatically turn on when the battery voltage discharges to the operator set point, triggering the fuel cell to automatically turn on and charge until it reaches the turn off voltage set point, as opposed to reaching those deep discharge amounts, having a load disconnect, and potentially damaging your batteries. SunWize and EFOY are here to assist you for an easy integration to size the components for a successful project. So looking at the diagram on the top left, you can see a scenario where the fuel cell is integrated with solar panels, the charge controller, and a battery to create a hybrid system. On the bottom left, you can see that in the green bar charts, that is the power production of the fuel cell, which is only designed to run during the months where there's the lowest solar insolation levels, November, December, January, February. The black line is your load, and the gray is the solar curve. This redundancy gives you 99.9% reliability, is weather independent, and has next to no emissions compared to a gas generator. So finally, looking at the various rated capacities of power output for these fuel cells on the left, you can see there are 45 watt base units that output 12 or 24 volts DC of power, 110 watt rated output for 12 or 24 volts DC of power, 220 watt rated output for 12 or 24 volts DC of power, and 500 watts rated output for 24 or 48 volts DC of power. We want to highlight that this technology has been proven with over 45,000 units deployed in various applications, some of which we call out above, such as SCADA PLCs, chemical injection pumps, security surveillance, instrumentation automation, valve control, communication equipment, and many, many others. So again, if there's any questions on this, I encourage you guys to reach out on chat. With that said, I'm going to turn it over to Brad to cover the topics on the Morningstar side of things. Thank you, Brad, and I'm going to give you control.
Okay, thanks very much, Errol. That was an excellent presentation, and just want to say that, you know, not only seeing the sizing equations and a lot of the math, but, you know, the tips and, you know, experience that comes out in a lot of the bullet points that can only really come from, you know, having been in the industry and having the experience that you guys have. So it's really great to see all this in the presentation. So thanks very much. Again, just to introduce myself quickly, my name is Brad Verwald. I'm product manager at Morningstar. I've been with the company for 18 years and proud to participate in this joint webinar with SunWize. And I'll be talking a little bit about the controllers now, specifically as it relates to some of the system sizing questions. So first, a little bit about Morningstar ourselves. We have about 4 million products in the field throughout our installation and manufacturing history, and that goes back to 1993. We have worked all over the world in more than 100 countries, and if you know something about our products and our various lines, they are kind of focused in a variety of applications and verticals, but we have worked in residential and rural electrification, specifically tackling one of the largest rural electrification projects in off-grid, which was a 200,000 home project in Peru with 3,000 community centers. We also cover commercial applications, and the particular focus of today is more on industrial applications such as telecom, oil and gas, and security. We think of ourselves as the charging experts, and as you've seen, there's a lot to discuss when it comes to battery charging, set points, decisions, current ratings, and all of that has to be taken into account in the product, because often the controller is the heart of the system and really has the information going in and out of it to make those decisions. So setting it up correctly and also making the right choice in charge controller is really important. And that's done after a lot of the load and system sizing that Errol and everyone has explained from SunWize is kind of the last decision that's made after the hard math has been calculated for the loads and for the site needs. One of the things that we're very proud of also is the lowest hardware failure rate in the industry, because we knew that these are very long life systems. They sometimes will see many battery cycles or replacements. The charge controller hopefully should be part of that system for, you know, many years, easily a decade or more, we hope. And one of the nice things of having 4 million products in the market is that, you know, we have seen a lot of these products go through their usable life, and we're happy to say that they are meeting our long life expectations. Okay, so moving forward here, we do have a couple of different product series available, and we have these available because of what I just mentioned, that we have both industrial applications as well as some differing needs in the rural electrification market. So what we did is we actually segmented the products. We have the Morningstar Professional Series, which is really your mission critical, high reliability, industrial focused products. And those are generally controllers that have more advanced features, better set point and programming capabilities, enhanced communications. Many times they'll have the certifications such as UL and IEC and hazardous locations that are required for the applications and industries that they're being used in. And then the Morningstar Essential Series, which really is still our core charging technology, the quality that we do put into the products and the circuitry to make sure you get that long life, but with a simpler subset of features, things that are maybe a little bit different from industrial, such as the USB charging you can see on the product featured there on the right, and just generally a more kind of economical application focus for that controller line. Okay, so going forward, what I'd like to talk a little bit about is, now that you've seen a lot of the math and work behind the system sizing that goes into calculating, what is needed at the site to power that off-grid load, I'll talk specifically about the last decision, which is often the charge controller, which brings it together, and some of the conditions and requirements of the specs for the controller that often go into this system. So I'll do a little bit different variation here on the power and talk generally when we see a requirement, it might have listings such as these items that are going to ask for specific specs to be met. Okay, so to go down this list, it would be up to a 60 amp maximum charging current based on what's needed to go into the battery. If the application is a 48 volt system, you'd of course have to have support for 48 volts because many are just 12 and 24 volt models. Often, I think the example given previously was utilizing 72 cell modules, the most common being either 36, 60, or 72. And that does have an impact on charging because you have to ensure that the module voltage is at least as high or considerably higher than the battery voltage in order for proper charging to take place. But as there are thousands, and I would say tens of thousands of modules in the market, you have to be sure that it's configured in such a way that throughout the entire year and throughout those temperature swings, that the voltage on the array will be sufficient to charge the battery in all cases. Okay, so we want to talk a little bit about that, and I'll be referring to a system string sizing tool that we offer for Morningstar a little bit later. Since a lot of these systems are usually my favorite place, the top of a mountain, for either reasons of data connectivity or just that's what the site conditions require for a specific load. You'll see that lightning is an ever-present problem, and having built-in transient surge protection is really critical, especially for the charge controller, which often seems to get the brunt of it, even from transients in the ground. Often certain accessories are required, such as alarm contactors for various fault or notification conditions, or if we're working with a hybrid power system, sometimes a little bit of inter-device communications required. We specifically see applications where protocols of a certain nature are also asked for at the site, because if it's going into an industrial or telecommunications application, requests for ModBus or SNMP protocol sometimes come along with the requirements. And then lastly, the ability to support a variety of accessories, generally something to provide system data, the interconnectivity of different charge controlling products at the same site, and of course, our relay driver product, which often adds the alarm contacting capabilities. Okay, so this would be a standard requirement here, the 60 amps, 48 volts, a very wide temperature range that the controller has to operate in, the auxiliary relay option as a need for, indicating a fault or communicating with other equipment at the site, which is very common. Compatibility with 60 cell modules, a significant amount of transient surge protection, in this case 4,500 watts is a decent threshold to hit, the communication requirements, and the accessories. So in this case, we'll talk about the TriStar MPPT 60M, which has those features enabled and has the data communications available and the compatibility with those accessories to meet those requirements. Okay, so I'll be talking about the TriStar MPPT 60 going forward, and a little bit about some of the details for that system. So first and foremost, as we just heard, a lot of the set points can vary greatly, and we have a lot of chemistries that can be supported for different battery types. gel, sealed, flooded, also AGM, and more recently lithium is being used more and more in pure off-grid applications and in wider temperature ranges. So one of the most important things to do is make sure that the controller can provide those settings, either with a variety of defaults that are built into the controller, or in this case, what we'll do is give an example of a customization that can be done to the controller from one of our battery partners. And those configuration files, as part of the Energy Storage Partner Program, are available on our website and are really directed towards the not so common chemistries where we have a variety of set points you can download and utilize. So putting those dip switches up 4, 5, and 6 puts the controller into a custom mode and allows you to use those configuration options. So what the Energy Storage Partner Program does is we've been in touch with a variety of manufacturers of different battery chemistries, and our app engineers talked to their app engineers, and we came to an agreement agreed upon between manufacturers of what those ideal set points would be in order to take good care of those batteries. And after that agreement was basically created in a configuration file, those are put on our website in order to give customers and system integrators and users the confidence that the system set points being used are ideal for that battery, okay? Because this is a big portion of what we talk about in our applications and technical support, is what settings should I use? So we're trying to provide a little bit more clarification and alignment in the industry with the Energy Storage Partner Program. So what you'll find is you can click on a variety of manufacturers and ever-growing lists on our website, and we can send you that information along with some tech write-ups that will explain, why some of these settings are needed and some of the models that are supported, and these sort of, a few gotcha cases of things to be careful about, such as temperature extremes or battery disconnect options that you want to be aware of before you size the system. Okay, and as I said, Energy Storage Partner Program is something that continues to grow, and look for more and more information on our website, and more often we are partnering with our distribution partners as well to make sure that we're all in alignment there. Okay, as I mentioned, the string calculator, another really crucial tool for sizing the products. And there's a lot of string sizers out there for the grid tie market, and it's very popular to use a variety of them. There's software tool packages you can purchase for PCs as well, the variety of them being web-based. But with the string calculator that Morningstar provides, it definitely has some uniqueness to it that makes it really specific for off-grid. We don't just size the string, we take into account the voltage of the battery, the depth of the battery discharge, in other words, the low voltage that it has to go down to, the peak voltage it may be charged to, accounting for temperature compensation. A very cold temperature battery is often, not exactly 12 volt nominal anymore. It could peak into the 15s if it's a lead acid battery. So we have to take all that into account. And then also we ask for the record low and the average high temperature, so that we can make sure that not only the battery's set point voltages, but also the impact on VMP and VOC of the array are also adjusted for. Because what you don't want is to have a voltage open circuit that looks great at 25C and realize in extreme cold that it exceeded the open circuit voltage rating of the charge controller and cause damage. So we're going to do all those checks for you with an analysis with the Morningstar string calculator. And one more pitch I'll make that is very handy reason to use this tool is that we have a professionally managed and subscribed to module database from industry professionals that do this and update it quarterly, during which we quickly import that database into our string calculator. So you're going to see the latest and greatest of the PV world represented in that database. Okay, moving on, a little bit about some of our accessories. As you saw in the request there for the spec compliance, the Ethernet MeterBus converter is a great product if you need to get IP-based data, either Modbus or SNMP, and then you can transport that data over a wireless connection or really any IP-based network. I hear great things are coming with satellite connectivity, which I'm excited about for off-grid because, as I said, we like mountaintops for our site locations, so there's lots happening there. But if you have IP-based data, you'll be able to transport it over all of those different mediums. And it's compatible with the majority of our product line, which is data enabled. In this case, you can see cloud connectivity easily provided using the Ethernet port. Here's an example of a ProStar MPPT. Pretty much any product of ours that has that RJ11 jack, which we call MeterBus, but has a dual purpose and that can also work as a serial connection, can talk to the EMC1 and give you that IP connectivity anywhere in the world. And I think that remote connectivity, monitoring, and management is really, whereas it was on the fringes of the most extreme applications in years prior, now is really becoming commonplace for a lot of these systems. And I like the example that SunWize covered with the power over Ethernet, because even the loads many times are Ethernet enabled devices. And it just so happens a lot of times security applications or telecom or point-to-point radios will use SNMP as a protocol to manage them and their bandwidth. And you can also manage the solar controller data using those same SNMP protocols. So there's a reason we were trying to align with that industry by choosing a common protocol. Okay, moving on. Also, we offer an MSC product, which is another type of adapter that will allow you to convert that MeterBus port on the product to a standard RS-232 serial port. So a variety of PLC and SCADA equipment do prefer that connectivity still. It's a simple point-to-point, very low cost when you just need to connect devices. And we also offer a similar version with RS-45 support, and that being also a serial protocol, but with the ability to talk to many devices on the RS-45 communications bus. So just a slight variant in that protocol, and we offer both of those solutions. Now, our MeterHub product is often specified in these sites if you're connecting multiple TriStars. We do typically scale this product sometimes to hundreds of amps for very large systems, and it does parallel very well. But you have to pay particular attention to not only the need to connect those devices together so that you can share metering information, but also one of the unique benefits that the MeterHub offers there in the last bullet is it provides isolation, or in this case, optical isolation of the ground for the data communications. And you may be wondering, why is that important? Well, obviously grounding is really critical, but in a lot of applications, the ground, you have to make sure you've got one single point to ground. And sometimes in telecom, the ground is actually on the positive and the system has been inversed. Now, we can be compatible with those systems, but one thing that many other competitors do not offer is isolated ground connections on your data communications ports. And if you happen to switch that ground, you can see current flow over your data lines, which is not something you want. Usually leads to burned out networking equipment. So the MeterHub provides that isolation as well. So next slide is talking a little bit about the relay driver. This actually uses that same RJ11 port as well. And this provides, I call this the Swiss Army knife. It's one product that just solves a lot of really common problems, such as when this voltage threshold is crossed, I want to close this switch, or I want to start this generator when this battery voltage gets to a certain point of depth of discharge. The relay driver handles all that with a fairly simple type of logic interface. And as I said, just solves a lot of useful problems. So you can specify the relay driver with a variety of relays and contactors to meet those needs. Okay, so that's just a brief overview here to finish out the presentation by covering some of the product features and decision making that goes into a charge controller. In summary, I just want to kind of state a few items that, what you've heard today, a lot of excellent information from SunWize and their partners, and looking even at the EFOY systems. Hybrid solutions are really a common application as well, and very typical in industrial, and they can actually enhance and work with the solar system to provide a lot of additional energy capacity when you need it the most, which is in cold weather. So understanding your load and system needs is first and foremost, knowing the constraints. Some customers have asked, what do you mean exactly by space and easement? When you have a lot of room available, but it's often not typically the case if you have a tight application where you need to be on the side of a highway, or you have limited space where the array can go. That's very common with telecom, which has sort of leased real estate implications as well. Lastly, determining, often in this order, the array, the battery size, and the charge controller requirements, all based on the needs of your loads. Keeping in mind your communication and protocol choices, which is becoming more and more common, and where you'll see a lot of continual improvement and enhancement in Morningstar's product line. As I said, consider hybrid systems when those are also beneficial, so that you don't need load control, but instead can manage those deep discharge periods with additional energy stored at the site. And then lastly, using the accessories, as I talked about, metering, relay contacts, and other types of adapters and connectivity, which is going to enhance your system functionality. Okay, so that's a summary of the presentation. Really a tough act to follow there, bringing up the finish here after all this experience. But with that, I will go to back to Mark and the rest of the team, and we can have a little bit of Q&A.
Hey, thanks, Brad. I've taken myself off mute, so hopefully you can hear me okay. Thanks also Errol and Grayson. And also, a great shout out here to the SunWize engineers who have been typing very quickly to answer a slew of questions that have come in. We must have like 30 questions that were answered via text directly to those people who asked those questions, but we do have some additional ones that just came in. So let me take a look at them. We have a question from Robert. Question is, are fuel cells used in colder, less sun environments, or also in areas like Arizona, New Mexico, and Texas? So I guess that would be for Errol or Grayson.
Yeah, and Dustin, actually, if you want to go ahead and take that as well, I'll let Dustin speak directly. The short answer is yes, based on a variety of applications. But Dustin, if you want to add some more, I'll let you take that away.
Okay, very good.
Hey.
Thanks. Oh, sorry, go ahead.
I wasn't sure if you wanted me to jump in or not, but
Sure.
yeah, absolutely. Fuel cells can be used in warmer climates. We just set them up a little bit differently to deal with the heat versus dealing with the cold weather.
Perfect. All right, I see a question coming in from Mark. Question is, since the TriStar controller needs to have a selection made for using it either as a charge controller or load controller, would it be feasible to use a SunSaver controller with the LVD feature as a disconnect means to protect a connected load from low voltage? And he says, understanding that the connected load would have to be properly sized ampere load for the SunSaver controller. So do you want to go ahead and take that one, Brad?
Sure. Yeah, that is a common application we see, is using basically the charger, the TriStar, which is a charger only in a lot of applications, or combining it with another TriStar that can handle the load control. But if you are at a lower voltage battery, such as 12 or 24 volts, and you've already got the charging needs taken care of, there's really no reason you can't add a SunSaver just as a load controller. It's very cost effective, definitely industrial design, and we've seen, let's say, an example of 40 amps of charging on a TriStar on the battery side, and at 12 volts, and then using just something as simple as a SunSaver 6L 12 volt on the load side for an LVD. It is a fixed LVD, there's just one setting, but generally it's sized, as Errol had said, for 80% depth of discharge, sort of out of the box. So if that meets your needs, then it's a great option, and something you can install. They can work together. So.
Okay, great. Thanks for that answer and question. I see a question from Jeffrey. This was already answered by Garrett, one of the engineers that's online with us, but let me ask this question. It's a nice question. Can you have full array power to the inverter when the battery is full? And Garrett is saying generally yes. So do we want Errol, Grayson, or Garrett to add anything additional to that?
Garrett, if you'd like to take yourself off mute, if you're available, you can go ahead and speak to that.
Yeah. When the batteries are full, if you're using an inverter, if the inverter has a controller on it, generally you're able to have the solar power, not have to have a disconnect or anything like that. Most controllers have the ability if the batteries are full, to protect themselves either by going open circuit or just disconnecting the circuit itself. So you shouldn't have any concerns with that.
Okay, very good. Thanks for that question and thanks for the answer.
Mark, if I could just jump in, one other thing on that is, yeah, depending on the controller, PWM controllers will almost completely go into an open circuit stage, meaning the array is just sitting there at that point, which is perfectly fine if the battery's topped up. And a PowerPoint tracker will push the PV array off the max power point in order to limit current. So both of those have an option to push that off. So yeah, there's never any concern once the battery's full. And then obviously that's where the controller is going to kick into that third charge stage that Errol showed earlier in the deck, which is the fluid stage.
Okay, great. And I see another question. This one's from Fernando. He asks, how many parallel battery strings would be the max advisable? And I see the answer from Kyle here. He said that we don't recommend more than 4 strings of batteries in parallel. So I think we got that question. Again, there's tons of questions here. I think we'd be all day if we verbally answered all of these, but we did text answers. Looks like we did that now to, looks like everybody that asked a question received a text answer to their question. I just wanted to pick off some of the questions that I think the whole audience would relate to. So I think we're pretty good here. Let me see, I just see, did I see one additional one coming in? A couple people asked questions about pricing and products, so you can just address them to SunWize and they would be able to help you with sourcing any of these products. So I think that pretty much covers it for today. Is there anything else that Brad, Grayson, or Errol would like to add, or anything that I might have missed? Any questions that you see that maybe we didn't answer? Or are we good?
I think I'm good from my end. I just want to thank everybody for the time and the questions, especially the application engineers on our side work in the chat. There's lots of channels to get with SunWize directly through our website, sunwize.com. So if there's any technical questions or any other needs, just feel free to reach out to us via any of our channels: phone number, chat, email, form submissions, etc.
All right, perfect. Why don't we go ahead and advance to the last slide, which is a thank you slide. And this last slide in the slide deck also has contact information for SunWize and Morningstar, website, phone number, and email. Certainly appreciate everyone's time today. Hey, thanks for all those great questions and the great answers. A lot of good information was shared here. We will do more of these webinars in the future, so stay tuned. Other than that, I'm going to conclude the broadcast and we'll see you next time. Thanks so much.
Thanks, everyone.